Okay. Well, let's go ahead and get started here. My name is Brian Ruff. I'm a PhD student at the University of Minnesota at the Department of Geography, Environment, and Society. And it's my pleasure today to introduce Jundong Qiao. Uh, what's really exciting to me, my little aside about this is, I've been following kind of the emergence of deep learning for the past couple of years. And, it's exciting to see this, these innovations start to be brought into agent-based modeling, so that and particularly related to the modeling of individual behavior. So a little bit of background on Jundong. He is a PhD student in environmental engineering at the University of Buffalo. He's trained as an environmental engineer, and his research focuses on building sustainable ecosystems by specifically designing fish passage structures. And the goal is to assist freshwater fish in migrating along hydrodynamic barriers and river systems. Currently, he's working on integrating computational fluid dynamic techniques and particle tracking, velocimetry, and deep learning techniques in order to develop an individual-based model that will learn and predict fish path choosing behavior. And with that, we'll do our ABM webinar silent clap to welcome Jundong to present to us.
Hello everyone, my name is Jundong. It's an honor for me to share my work here. Today, what I'm going to talk about is an ongoing work, which is also part of my PhD project. It is deep learning in individual-based modeling, an application of convolutional neural network in fish path choosing behavior. First of all, I'd like to introduce the outline of today's talk. It will include motivation and background information, model development, the proof of concept, and what I'm doing for this project currently, and I will summarize today's talk. So, as the title suggests, it's a project about fish. Let's take a look at a basic life cycle of a stream fish. Fish usually have a spawning habitat, feeding habitat, and also refugium from harsh environmental conditions. Naturally, the fish can migrate between these habitats at different life stages accordingly. However, human activities such as dredging and artificial constructions, such as dam construction, will apply a negative influence or simply impede the movement of fish. These are common forms of disruption of river connectivity. Therefore, it is imperative to take measures to migrate the river connectivity disruptions. One measure to mitigate the river connectivity disruption is to design fish passages. So the fish can migrate upstream or downstream accordingly. These pictures show the different types of fish passage that can be designed and installed alongside a dam construction in the middle of a river. So the fish can get through this area to upstream mostly. When it comes to our project, the research subject is demo shiners, as you can see from this picture. It's kind of a small fish. Demo shiners are important native prey species that fills the food web of the Niagara River ecosystem. Also, it's also a vital food source for this common tern. The common tern is a threatened species in neural state. Also, the migratory such as bald eagle prey on the animal shiners. So, the health of animal shiners play a significant role in the local ecosystem in Niagara River. Here's a study site for the project. The Niagara River starts from the Lake Erie, ends at the Lake Ontario, and in the upper Niagara River there is a Squaw Island. On the Squaw Island there is a Bulgarian Park. So along the seawall of the Bulgarian Park, the historical channel modification and shoreline alteration increased the water velocity so high so that the animal shiners in this downstream end cannot pass through this area. As you can see from this on-site picture, there are a large number of shiners schooling here. They attempt to swim upstream to Lake Erie. However, they couldn't pass through this area because the velocity is over 1 meter per second. It is too high for a fish like animal shiners with a body length only 2 to 3 inches. So there is a great interest of building a fish passage along this seawall to assist animal shiners to swim to the Lake Erie and complete the migrating circle for them. So in this webinar, I'm not going to talk about the fish passage design. However, I want to emphasize the importance of the evaluation of fish passage because a large number of research have shown that a lot of fish passage which were installed in the last 50 years failed. In some extreme case, the fish passage shows zero passage efficiency, which indicates that the design of the facility did not work as it is supposed to do. So it is necessary to evaluate fish passage efficiency before the installation. For doing so, there are two questions need to be answered. One is, will the fish pass through the designated passage? If so, how efficient it is? To answer these two questions, IBM model, the individual-based model, comes to play. The individual-based model is expected to evaluate the fish passage efficiency numerically. Next, I'd like to talk about how the individual-based model look like. The individual-based model in this study consists two distinct models. One is CFD, one is CNN. CFD stands for computational fluid dynamics, which will produce a continuous flow environment for the study site. The CNN stands for convolutional neural network. A well-trained CNN is considered as a smart virtual fish. Then the coupling of the CFD model and the CNN network will consist this IBM model. Of course, for training the CNN, we need training data. So the PDV technique will be used here to provide the training data for our IBM model. Next, I will talk about each component and how they are developed, and then how they work together to form this IBM model. First of all, let's take a look at the component A, our CFD model. I'm not going into the details about the development of this CFD. All you need to understand is it provides environment for the virtual fish at any given instant. The environment information for the virtual fish will be expressed or will be described in terms of velocity, vorticity, turbulence intensity, or turbulence kinetic energy, and so on. As shown in this picture, a CFD model can provide the information, also the vorticity information in a complex flow environment. The fish can make decisions according to the perceived information in terms of the flow environment, and then to demonstrate its behavior accordingly. So when it comes to fish behavior, we should ask, what is behavior first? So generally, behavior is how animals interact with its environment in a physical or psychological way. Hogan provides this structure to describe the behavior system. There are three building blocks: the perception mechanism, the central mechanism, and the motor mechanism. With this conception of the behavioral systems, animal behaviorists like to know the cause behind the behavior at a given moment and environment. Motivation is usually considered to be a very significant explanatory variable. An example is an animal will look for food if it is very hungry. So there is a motivation for certain behavior. Another question is how a behavior develops. This is a problem on the development of behavior mechanism from early stage to maturity. Specifically, it is about a certain behavior is learned while the animal is interacting with its environment. So there are many types of fish behavior, such as swimming, feeding, predator avoidance, and interspecies interaction. For the purpose of testing the fish capacity efficiency, as I emphasized for this project, only fish constitution behavior is considered in this study. In the 2D domain, the flow environment is characterized in terms of the turbulence, kinetic energy, vorticity, vapor stress distribution. The fish will perceive this information and make a decision. In the 2D domain, the fish constitution behavior is classified into 8 choices surrounding this fish. It either goes straight forward, or make right decision, make left decision, or going backward, as shown in this plot. The distribution of the TKE, vorticity, and vapor stress are the environmental variables taken into account. In literature, there are studies that focus on fish choosing behavior in water body or simply in fish passages. Andrew Goodwin developed the eland model to predict the fish behavior in front water of a dam. The eland stands for 11 Lagrange agent method. The authors simplified the fish environment into stream, velocity gradients, and pressure gradient. The fish movement mechanism is predefined by the authors. In 2016, another group of researchers, Qiao et al., applied a similar idea to develop of fish behavior in a vertical slot fish passage in the 2D domain. While Andrew Goodman and his colleagues believe that the fish is only sensitive to the strain and velocity gradient and pressure gradient, Gao and his colleagues conclude that the fish is only sensitive to the TKE distribution. As shown in this picture, the fish only choose the area with magnitude of turbine kinetic energy between 1 to 1.3 joule per kilogram. So both of the models predetermine the behavior rules for the target fish to follow. All the rules are from various observations on different types of fish. Therefore, it's not actually unexpected that these researchers choose different parameters to represent the environment around the fish. An alternative to the previous deterministic model is to develop a behavior map in the sense of ontogeny for the species of interest, which means to develop a specific behavior map of the target fish by learning from fish experience. By adopting the conception of a behavior system proposed by Hogan, as I showed in the previous slide, the overall structure of the behavior map is as shown in this schematic plot. The sensory system will perceive the external sunlight, stimuli, and the output from the sensory perception will be integrated in the central part. Eventually, the behavior of the behavior signal will be generated by the motor mechanism. During the development, the central part will evolve with time and experience. In addition, animals really act different to the same or similar external stimuli. So there is a random factor for the animal behavior. One remedy for accounting for the stochastic nature of the fish behavior is to add a random number, epsilon here, which is drawn from a standard normal distribution. This coefficient sigma is used to regulate the significance of the randomness. A virtual fish is a well-trained convolutional network, needs to learn from real fish, so we need to know how a real fish perceives environmental information. Fish is kind of a multimodal sensory organism, so hearing, lateral line system, occasion, taste, and visual will provide stimuli on the fish on certain behaviors. Usually, for the fish movement behavior, the visual and lateral line system play more important roles. So in this study, only the lateral line system perception is considered as an external hydrodynamic stimuli, since I'm a CFD person before doing this work. So the lateral line of most fish, actually, as you can see, the lateral line system of most fish consists under the superficial neural mass on the head and also the fish trunk. In addition, many fish have neural mass embedded in the lateral line system. It is underneath skin or it is on the surface of the skin. The lateral line system can receive hydrodynamic information from its surrounding habitat. Biologically, the fish is able to sense the vortex in the water environment. Also, the canal neural mass in the lateral line system can serve as a high-pass filter, which refines the perceived signals. An important issue for developing an architecture of behavior map is to build into the prior information in the model. Here, the model is a convolutional neural network. The convolutional network is chosen for this reason because the convolution process is for detecting the local features that may excite neurons. Just like the neurons in the lateral line system can detect the vortex, the local structures. Also, the mass sampling process in the convolutional neural network can mimic the information filtering process in the similar way that the canal neural masses do. So here's an overall structure, base structure actually, for the neural network. After several rounds of convolutional operation and sampling, the fading signal will be integrated into the neurons. So a neuron is essentially an information processing unit that is fundamental to a neural network. There are three building blocks for neuron, or three elements for neuron: the input, an adder, and activation function. The activation function produces the output, which can be integrated by the neuron in the next level. At the end, the neuron responsible for the motor mechanism will compute the probability of actions given the external stimuli. As we all know, a neural network will need a lot of training data. So I'm collecting the training data in the lab. Here's the schematic of the experimental setup. In the lab, there's a film. All of the black dots represent the particles I'm going to use to track the flow motion. The fish will be introduced into the flume. During the experiments, the real fish trajectory in the flume and the particles will be recorded by the overhead camera. So after collecting the images by the camera, the data analysis goes to two aspects. One is the velocity calculation using the PTV technique. One is the fish trajectory identification using the motion detection technique. For the PTV, the particles will be identified based on the raw images, so instantaneous velocity can be calculated based on it. Using the background subtraction technique to identify the fish in the same set of images. So the fish locations and the coordinates in each single image can be returned step by step. So here's an example of fish tracking based on video from a previous fish study. So clearly, the technique can return the needed fish locations. So from here, the environment information for the fish in terms of instantaneous velocity field, and also the aging information, the fish pasturation behavior can be obtained from the lab. So After collecting all of the training data, all of the data will be fed into the neural network, and the neural network will learn from the environment information in terms of velocity, TK, verticity, and so on. It will learn from this experience to make final decisions like a real fish do. So after training, to connect the CFD model to the convolutional neural network, which is called smart virtual fish after it's trained, to form an individual-based model. The individual-based model can be used to test the fish behavior numerically. So in a CFD model, the 2D domain is defined by a Greek word. And computed hydrodynamic variables are defined in the center of the Greek word. Like the virtual fish uses the same Greek centers as its location by given moment as well. So assuming the virtual fish swim at a constant speed and make decisions at each cell in the Greek word center, so its decision-making frequency will be defined by the ratio of swimming velocity over these ice. This is also the frequency for the CFD model simulation to store its results and produce environmental information for smart virtual fish. So while the CFD model and the CNN are coupled, the virtual fish is set in a random location in the invariant field produced by CFD model, and then the virtual fish will make a decision to move based on the trained convolutional neural network and its received hydrodynamic stimuli. The movement decision will take it to a new location in the invariant field. Then the new stimuli around the new location will trigger a sequence of movement action. So this is overall the structure of the individual-based model. Like I mentioned before I started, this is an ongoing work. I'm still working on collecting data for the convolutional neural network in the lab. But I want to prove the concept. So I borrow some data from a colleague to prove the concept of IBM model. In this part here, the y-axis just indicates the width of a flume. The x-axis indicates the length of the flume. The two black rectangles indicates the flux in the flume that create the compact flow environment for the fish. The black triangle indicates the recorded fish trajectory, or other trajectories otherwise predicted by the convolutional neural network. Since I only use 150 examples for the neural network to learn, there are only 100 data points and for the validation and 100 data points for the test data set. But I believe from this simple example, I believe the convolutional neural network is able to learn features from the input variables and make reasonable predictions. Of course, as we know, the size of a training data set in this process is too small for good results. So the large data sets are needed. That is what I'm doing currently in the lab. So yeah, I'm collecting the training data for the convolutional neural network. Here are several snapshots from the images. So here I have the trapezoidal wedge in a flume to create complex flow in the flume with particles on the water surface to track the flow environment. In the meantime, the fish the fish are pretty small, but if you have a bigger screen, probably you can see it. Yeah, the fish trajectory will be recorded. The more training data collected, the more accurate the virtual fish decision-making action will be in the future. So, yeah, this is still ongoing. So, to summarize what I just talked about is convolutional neural network shows potential to learn and predict fish catch-shooting behavior in the 2D domain. And also, it has a biological basis. Couple the CFD model and the CNN model can form an individual-based model that is used for fish passage, pre-evaluation. I think that'll be all for today's talk. Take questions. Thank you.
Wonderful. Thank you so much. So we'll open up for questions now. I've got a bunch of questions here now, but let's see if anyone else has any questions. Oh, Gian has a question here in the comments.
The question is, fish movement seems to have a certain pattern. So, do you consider about pattern recognition to validate the model? Yes. The training of the convolutional neural network per se is a pattern recognition process, I believe. I'm going to use different steps of a fish trajectory to validate the trained convolutional neural network model. So, did I answer the question, or do you need otherwise? Any other questions?
One thing that I was wondering is, you're doing everything in two-dimensional environment, and I'm wondering, I don't know much about modeling, fish and individual-based models, and so please forgive me if this is naive, but could you speculate a little bit about other results you've seen if it were to be translated into three-dimensional environment? How would that change maybe the behavior that you're observing, or obviously the problem complexity would be much more, but I just would love to hear your comment on that.
Yeah, the complexity will grab a lot. This 2D model, I believe it's just a starting point for this direction. So it's always easier to start from 2D modeling. For one reason, we're using the 2D modeling either for the CFD model or for the fish behavior observation is for the study side in this project. The flow pattern is not complex in a vertical direction. So it's more varying varies in the 2D domain, in the horizontal plane. So we decided to use a 2D model to simulate the real water flow motion, the river. Another problem is for the fish. Um, from our observation, of course, there are 3D movement for the fish in the river. However, the majority of the fish like to swim at a certain level, which is about 2 feet below the water surface. That's where they hang out, where they migrate. So, yeah, it is a simplification for the real 3D case, but we believe to very most extent, our model will explain the fish behavior. Yeah.
One other question that I had was,